many finite difference scheme, explicit or implicit type, for the partial differential equations. So I am going to continue that study with the brief idea of truncation error, consistency, stability, and convergence. My slides are visible to you. Okay. So with the help of a simple finite forward time central space scheme for heat conduction equation, I will introduce the concept of consistency, convergence, and stability. So it is well known that there are three fundamental properties which should satisfy every finite difference scheme for a given partial differential equations, which are consistency, convergence, and stability. So we know that consistency roughly implies that a finite difference approximation or finite difference equation is a good approximation of the given partial differential equation operator. While convergence implies that the solution of the difference equation approaches to the solution of the partial differential equation if the computational mesh is going to refine. Whereas stability implies that solution of the differential equation is not too sensitive with respect to the initial data, means that if we change some small changes in the initial data, then there should not be large variation in your numerical solution. So it means that solution of finite difference scheme should not be much sensitive towards the small perturbation in the initial data. So theoretically, we will discuss each thing in today's lecture. So these concept of consistency, stability, and convergence we will develop with the discussion of a simple forward time central space scheme for this 1D parabolic problem. That 1D parabolic problem is nothing that is a heat conduction problem where that function u represent the temperature at a position x and time t, while ut represent the rate of change of temperature with respect to time at a point, and uxx represent the curvature of the temperature for profile, where sigma is the thermal diffusivity, which is defined by K upon rho C, where K is the thermal conductivity, rho is the density of the material, and C is the specific heat capacity of the material. So in this lecture, we are not aimed to discuss the physics of this heat conduction problem. Just I am giving you a small idea about this. Here, thermal diffusivity, that is that parameter sigma, indicate that how quickly temperature changes propagates through the material. So for this heat conduction problem, we try to construct a simple forward time central space finite difference scheme. So to develop a FTCS finite difference scheme, first we partition the rectangular domain into some small subdomains by introducing a uniform mesh with spacing delta x equal to 1 upon j, where j is greater than 0 and j denote the number of mesh points or number of mesh intervals in the space direction, while time domain is partitioned with the mesh spacing delta t. So thus we introduce that kind of mesh over the rectangular domain. That x-axis represent the spatial domain, and this y-axis represent the time domain. So we are having j points in the space, and so on. We are having this time level. This is the zeroth time level, This is the first time level, this is the second time level, and so on. This is the nth time level. So this point represent the jth point in the space direction and nth at nth time level. Jth point in the space direction at nth time level. So this is the computational grid, so which we are using to construct the finite difference scheme. So it means that we are having a rectangular domain, and final time t we consider as some final time which we denote by capital T. Okay. So to construct this finite difference scheme, we replace the partial derivative by forward time and central space to obtain this one. So note that first time derivative we are replacing with this forward difference approximation. So this is the truncation error term in our approximation while we are replacing ut by this forward difference approximation. And second derivative term uxx will replaced by this thing, and here this is the truncation error in the approximation of uxx. So it's clear that xi lie in between -1 to 1 and theta lie in between 0 to 1, because this is the center difference operator. So that's why that error terms for that error terms xi takes the value in between -1 to 1. So about the construction of finite difference operator and corresponding truncation error term, I already discussed in the last lecture. So using the same thing, we are constructing this forward time central space scheme. Now, neglecting the discretization error term, we get this finite difference scheme where capital U represent the capital U with this represent the solution of finite difference scheme at the point xj tn. So UJN basically is the solution of finite difference scheme at the point xj tn. So this is our final finite difference scheme, and simplifying it, this finite difference scheme can be written in this form: use a n plus 1 equal to r use a minus 1 n plus 1 minus 2 r use a n plus r use a plus 1 n. So it's clear that from the construction of this forward time central space scheme, it is of explicit time. So we may construct an implicit scheme. So in that case, that right hand side, this approximation we will take at the nth n plus 1 at time level instead of nth time level. So in that case we can get the implicit finite difference scheme. And I think Professor Vivek already discussed that implicit finite difference scheme is unconditionally stable, while this explicit finite difference scheme will be conditionally stable, which I will discuss. Because here stability of this FTCS scheme depend on this parameter r equal to sigma delta t over delta x square. R should be less than 1, and this condition imply a severe restriction on the time stepping. So according to this restriction, delta t should be less than delta x square upon sigma, or roughly speaking delta t should be of order of delta x square. So with this restriction, r should be less than 1. That implies that over time space, time stepping should be very small, because delta x is already very small and square of it will be less than that. So delta t should be of order of delta x square. So if your mass is very fine in the time direction, only in that case this forward time central space scheme will converge, otherwise not. So this is the computational stencil for the forward time central space scheme. So it's clear that to obtain the solution at the n plus 1 th time level, we require information at nth time level at the xj minus 1 point, xj point, xj plus 1 point. So using this information at nth time level, we are able to get the information about the solution at n plus 1 th time level at xj point. While in the implicit scheme, that is, we have different thing. In implicit scheme, we have information only about xjtn point, and with the help of this, we try to find out solution at xjtn plus 1 point with the help of xj minus 1, tn plus 1, xj plus 1, tn plus 1. So computational stencil for the implicit scheme will be that kind. So just I am focusing right now with FTCS scheme. So let me so we can continue with FTCS scheme right now. Now question is that what is the local discretization error? So to analyze the consistency of a given finite difference scheme, first we need to find out the local truncation error. Local truncation error is defined in this way. Suppose we are having a differential equation pu equal to 0, and a finite difference approximation of it is given by p delta u equal to 0, where u is the solution of the finite difference scheme and small u is the over analytical solution for the given partial differential equation. If v is any smooth function, then the local discretization or local truncation error is defined by this equation, denoted by tau j n and defined by pv j delta x and delta t, that is p is over given continuous differential operator, v the value of that smooth function at the point at xj tn point, j delta x means that xj point, and n delta t means that tn. So this means xj tn point minus p delta v j delta x and t. So this is the definition of local truncation error. And if local truncation error approaches to 0 as mesh spacing delta x delta t approaches to 0, then we can say that our constructed finite difference scheme is in good agreement with the continuous problem. So that is the basic idea of the consistency. So for example, for the discussed heat conduction problem and corresponding FTCS scheme, our differential operator is this: PV equal to VT minus sigma VXX. Just 1 minute. Just wait for a 1 minute. Okay. So for discussed heat conduction problem, our differential operator P is defined by this VT minus sigma VXX, and corresponding difference operator P delta V is this: Vj n plus 1 minus Vjn upon delta t equal to sigma Vj plus 1 n minus 2 Vjn plus Vj minus 1 n upon delta x square. So is there any doubt or any query till now? Any query participants till now? Okay. So I believe Professor Vivek already discussed the construction of this FTCS scheme. So I am not giving much emphasis to construction of this scheme. Just I am taking it as an example to describe the local discretization error. Okay. Now, as per the above definition, local discretization error for FTCS scheme is can be calculated in this way. That is differential operator at the j nth point, that is xj tnth point, minus that difference operator at xj tn point. At xj tn point, difference operator will take this form. Now, further, it can be written as with the uh, uh, component wise of differential operator Vt minus Vjn plus 1 minus Vjn upon delta t, del V over del t over Jn minus sigma. Sigma you can take common outside, and it can be written as Vxx at Jnth point minus this one. Now we already know that V is a continuous function. So difference between them will equal to the corresponding truncation error term in the approximation of the derivative term. Similarly, that delta x square upon 12 with fourth derivative of v at j plus I nth, that is the truncation error correspond to discretization of this double derivative term with this one. So overall truncation error we obtain by this tau jn equal to minus delta t by 2 vtt j n plus n theta plus sigma delta x square upon 12 vxx j plus I upon n, where sigma is the thermal diffusivity as we discussed. Now, if V is the solution U of the given PD, then truncation error term will take that form. So that is the truncation error or local discretization error estimate for the FTCS scheme for heat conduction problem. Now, many literature discuss consistency in terms of local error. So, and although most of the literature defined consistency in terms of local discretization or error only, but few literature define consistency in terms of local error. So I will give you both the definition of consistency in terms of local discretization error and local error as well. So local error is defined with this difference uj n plus 1 minus uj n plus 1, where small u is the continuous solution at xj tn plus 1 point, and minus u, this capital U is uj n plus 1 is the solution of difference equation at xj tn plus 1 point. So that difference define the local error provided that there is no error period to the time level n plus 1, because we are having different time level like this. This is the initial time level, and also note that those initial and boundary conditions, initial or boundary conditions which these initial and boundary conditions are prescribed on this boundary of the domain. Initial boundary condition prescribed at 0th time level, and boundary condition are prescribed at both the boundary of the domain. So local error is defined with with this difference, and assuming that there is no error committed period to the time level n plus 1. So for the, if there is no error period to the time level n plus 1, so what does it mean? It means that at the time level 0, 1, 2 up to n, we are having solution of difference equation is equal to the solution of the continuous problem, that is Ujn equal to Ujn. If we commit no error prior to time level, then we are having ujan equal to small ujan and j run for 0 to j. So then above finite difference scheme will take this form. Use a n plus 1, that is the solution of difference scheme at the n plus 1th time level, minus use n, because prior to that time level use n equal to use n. So all those capital U can be replaced by small u prior to that time level. So difference scheme will take that form by replacing capital U by small u. Now in the last equation, in equation number 5, we already said that in equation number 5, if we replaced V with the solution U of the heat conduction problem, then solution U satisfy the heat conduction equation ut minus sigma uxx. So del V over del T minus sigma del square V U over del x square at the jnth point will be equal to 0. If you replaced here in equation number 5, replace V by the continuous solution U. And U, of course, is the continuous solution of the heat conduction equation ut minus sigma uxx equal to 0. So definitely you will satisfy that equation at each time level and at each point of the domain. So definitely solution U will satisfy that heat conduction equation at the point xj tn as well. So in that case, if we replace V by U, then truncation error will take this form. Tau Jn equal to minus Ujn plus 1 minus Ujn upon delta t plus sigma Uj plus 1n minus 2 Ujn plus Uj minus 1 upon delta x square. Okay. Now subtracting this equation from this equation, we are getting, consider combining this equation and this equation, of course subtracting the this one from this equation, we are getting Ujn plus 1 minus Ujn plus 1 equal to minus delta t tau Jn, because all other term will be cancelled out. This will be cancelled out if we combine both if we sorry if we add both the equation. So all things this term will be cancelled out and also this will be cancelled out. Minus Ujn upon delta t, minus is here outside, so that term also cancel out. So it remain with us Ujn plus 1 upon delta t minus Ujn plus 1 over delta t is equal to tau jn. So ultimately we are having this equation Ujn plus 1 minus Ujn plus 1 equal to minus delta t tau jn. So this is the estimate of local error for the FTCS scheme for the heat conduction problem. And note that that kind of relationship satisfied by all almost all explicit finite difference scheme. And here one can notice that local error here is defined by the negative of the truncation error multiplied by the time step delta t. So this relationship between local and local discretization error here, tau jn is the local discretization error. Ujn plus 1 minus capital Ujn plus 1, this is the local error. So this relationship between local and local discretization error generally holds for explicit finite difference scheme. So derivation of this local error is clear to you. Ankita, Brinda, is there any doubt? So definition of local error and local discretization error is clear. Okay. Now I already said that a difference operator or difference scheme P delta U Z n equal to 0 is consistent with the given PD PU equal to 0 if local discretization error tends to 0 as delta x approaches to 0 and delta t approaches to 0. That is, that truncation error tau Zn approaches to 0 while we are making delta x approaches to 0 and delta t equal to 0. For example, for the above FTCS scheme, we can see that local discretization error tau Zn approaches to 0 as delta x delta t approaches to 0. Am I right? So what, roughly speaking, what is the meaning of consistency? You have a continuous problem which we are defining by pu equal to 0, and correspond to that we are having a finite difference scheme p delta u z n equal to 0. So we can say that finite difference scheme is consistent with the given pd if both are in good agreement. That is, if delta x and delta t approaches to 0, then roughly speaking both are approaches to same operator. Am I right? So an equivalent definition of consistency we can give in terms of local error. So a finite difference scheme is said to be consistent if the local error tends to 0 at least order of delta t as delta x approaches to 0 and delta t approaches to 0. For the constructed FTCS scheme, we are we said that local error is equal to minus delta t tau Zn. Am I right? And one can notice that as delta x delta t approaches to 0, that minus delta t tau Zn also approaches to 0. So in terms of local error, consistency can be proven in this way. So either to prove consistency, either you may use the local discretization error estimates or local truncation error estimates, or you can use the local error estimates. But it is widely common to use the local discretization error or local truncation error estimates to prove the consistency. Okay. Next, we are going to discuss stability. Stability means that we are looking that our solution of finite difference scheme is not too much sensitive towards the small changes in the initial data. Am I right? Initial data is prescribed at the initial time level t equal to 0. So to emphasize that time dependency of the PD, we switch the notation of differential equation pu equal to 0 to this notation ut equal to lu, where lu is nothing, l is the spatial differential operator. That is, in our case, we are having this equation, heat conduction equation ut minus sigma uxx equal to 0. So in our case, lu equal to sigma uxx. Am I right? And note that if you we recall the classical theory of partial differential equations, it is well known that solution u of any given PD considered as an element of a function space. Here we will not go in detail about the discussion about the whole classical theory of partial differential equations, theory of function space, but simply we can note that always there is a scalar which is called a norm for a given element of a function space, and that scalar is called norm, and this is associated with the element of a function space, and that scalar is used to measure the size of the functions, size of the member functions of the function space, and distances between two functions in function space. So basically over the function space, And I believe all of you are well aware with this definition of norm. The norm u of a function u is a scalar that satisfies these three conditions. Norm u is greater than equal to 0, and norm u equal to 0 if and only if u equal to 0. Norm alpha u is equal to mod alpha norm u for any constant alpha, that is homogeneity condition. And norm u plus v should be less than equal to norm u plus norm v, which is a triangle inequality. So if any scalar which we denote by this notation, if any scalar, basically that norm is a function from function space to R. So if any function from function space to R satisfy these three properties, then that function or that is said to be norm, and that norm lie in the so in this way we can define the norm. Also note that with the definition of norm we can basically are able to define various kind of norms, but we are restricted here ourselves with two norms. One is maximum norm and another is Euclidean norm or L2 norm. Maximum norm is defined by this norm of u, which is maximum norm is we use this notation to define the maximum norm, and it is defined by maximum of absolute value of uxt x belongs to omega. Note that that maximum is taken over the spatial domain only. And in the same manner, Euclidean norm is defined square root of integral of square of uxt, and note that that integral is taken over the spatial domain only. So because of we are considering that we are estimating these norms at each time level. So while solution u of the PD, as I discussed, solution u of PD we considered as an element of a function space, we may think the finite difference solution as element of a linear vector space. Am I right? So to this end, we collect all unknown at a given time level n into a vector form. So suppose we are having this nth time level. So nth time level, we are having jth mass points in the space direction. So at 0th mass points, we know what is the solution u0n through the boundary condition. So what over unknown u1n, u2n, uzn minus 1, and so on un0, u1, uzn, uzn also we know by the prescribed boundary conditions on the right hand side of the domain. So basically unknown at the nth time level, we are having these elements u1n, u2n, uj minus 1n. So we can club them as a vector un together, and we consider un is a member of a linear vector space. So like we define the norm over the function space, we can define norm over the linear vector space. So we or you already know. So same kind of property if any scalar from Rn to R satisfy the same kind of property, that is norm of capital U is greater than equal to 0, all three properties satisfy, then that scalar is said to be norm for the linear vector space. All of you already studied these norm defined on linear vector space in inner product space in the linear algebra, so just we are using that definition. So using these notations, we can write the finite difference approximation as a matrix equation of the form un plus 1 equal to L delta un. And if boundary conditions are homogeneous, then we can get the inhomogeneous difference equation of that kind of form. Un plus 1 equal to L delta Un plus Fn. Fn correspond to the non-homogeneous boundary conditions. So you can get that vector Fn correspond to that. So for our constructed FTCS scheme, vector Un plus 1 will be this, and matrix L delta will take that form. This is again a triangular matrix, and this vector Un, if for the sake of simplicity we are considering that our boundary conditions are homogeneous, so our FTCS scheme will take that form. Am I right? Because look at this our scheme. Use a n plus 1 r use a minus 1 plus 1 minus 2 r use a n plus r use a plus 1 n j equal to 1 to j minus 1 to j minus 1. So at each time level n, we are getting that kind of triangular matrix because of these elements. And this is the initial conditions prescribed at the 0th time level, and boundary conditions we are taken homogeneous. So that's why that vector Fn in our case is 0. That is, our scheme in matrix form can be written in this way. Okay. Also note that property of norm over a vector space are identical to those for the function space. I already said that these three conditions which are satisfied by the in the definition of norm for a function space, if same kind of properties are satisfied by the element define satisfy over the linear vector space, then that scalar is said to be norm over the vector space. So that's why we will not repeat them again over here. So again, the two norms that are most suited for our purpose, the one is the maximum norm, for which is defined by this norm un infinity equal to maximum of absolute value of ujan. That is, for example, if you are having this vector 1 4 5, 1 4 minus 5, three-dimensional vector, what is the maximum norm of this? Maximum norm of this is equal to 5, and the distance norm, that is Euclidean or L2 norm. L2 norm is defined in this way for a given vector un. Summation j square of ujan square root of summation ujan square 2. So for that, L2 norm will be equal to square root of 1 square plus 16 plus 25. So in this way, we can define vector norm. Now, in the stability analysis for a given finite difference scheme, we try to measure the growth of the size of a matrix. So in that case, it is become necessary to introduce the matrix norm. So matrix norm provide estimate of the size of the discrete operator L delta. L delta here is a matrix, and the growth or decay of vector un with time stepping with correspond to different time level n. So here matrix norm again satisfy all those property which we discussed for the norm over the function space, norm over the vector space. But in addition, matrix norm satisfy one more additional property which is given by this for any matrix A and B. So here matrix norm is nothing that is a scalar from the set of all real matrices to R. So in addition those three properties, matrix norm satisfy one more additional property which is given by this norm of AB should be less than equal to norm of A, norm of B for any matrix AB. So maximum norm over the matrix is defined by this maximum of j mod aij, and then take the maximum over the uh, maximum over the each row. So this norm a infinity is defined as a row sum norm. So basically, if you are having, for example, this 2 by 2 matrix, 2 minus 4, 5 minus 6. Am I right? Okay. So to find the maximum norm, first we add each entry, absolute value of each entry of for each row. So for first row, we are having mod 2 plus minus 4. For second row, we have mod 5 plus mod minus 6. Am I right? So summation j mod of aij. And then we consider the maximum over each over the row. So what is the maximum of them? Mode of minus 4 plus mode of 2, that is equal to 6. Mode of minus 6 plus mode of 5, that is equal to 11. So maximum norm for this matrix is equal to 11. So that's why this norm is also said to be row sum norm, because we add absolute value correspond to each row and then find out which is the maximum among them. So in this way, an infinity norm for a matrix is defined. And L2 norm for a matrix is defined as a square root of spectral radius of the matrix A transpose A. Spectral radius of a matrix is defined by the maximum largest eigenvalue in magnitude. Am I right? So two norm for a matrix is defined by the square root of spectral radius of matrix A transpose A, and spectral radius is defined as a largest eigenvalue in magnitude for a given matrix. So in this way, infinity norm and Euclidean norm can be defined for a given matrix. So as I already discussed that matrix norm provide estimate of the size of the discrete operator L delta and the growth of decay of Un. The matrix norm satisfy the property of a vector norm as well as norm AB less than equal to norm A into norm B for any matrix AB. So for example, for the constructed FTCS scheme, matrix L delta is a entries, a tridiagonal matrix where on the diagonal we are having entries 1 minus 2r, and on lower and upper subdiagonal we are having entries r. So infinity norm, as we define for a matrix, infinity norm for the matrix L delta will be equal to absolute value of 1 minus 2r plus absolute value of r plus absolute value of r. R is positive, so absolute value of 1 minus 2r plus 2r. So note that if r less than equal to 1 by 2, then 1 minus 2r is greater than equal to 0. So in that case, infinity norm for matrix L delta is equal to 1. Okay. So with this preliminary consideration established, we define the concept of convergence and stability for the finite difference scheme. So far, I have not discussed about the definition of stability. So just uh, I define the vector, I define the function norm, that norm we required for the continuous solution small u, vector norm, that norm I need for the finite difference solution vector capital U, and matrix norm. So we can say that a finite difference approximation converts to the solution of PD on some finite time domain 0 to capital T is the final time in a particular vector norm if norm of un minus un approaches to 0, that is difference between the continuous solution and So difference solution vector u at any time level approaches to zero in some particular vector known as n tending to infinity. Delta x approaches to zero, delta t approaches to zero. Then we can say that over finite difference scheme converges to the continuous solution u over the domain this. So here the vector is un is the restriction of the continuous solution uxtn to the mesh. Am I right? Because what is capital, note that what is capital un vector? Un vector is this u1n, u2n, and so on, uj minus 1n. So un, that u is a continuous solution. So it means that un is nothing, that is u x1 tn, u2 u x2 tn, and so on u xj minus 1 tn at the point x1 x2 and xj minus 1. So that vector for the continuous solution you can obtain in this way. So this definition for the convergence is clear. Participants, this definition is any doubt, any query? Okay. Now we are coming to define the most important concept of stability for a given finite difference scheme. To define stability, let us assume that this vector un and vector vn at the nth time level satisfy the homogeneous finite difference initial value problem with different initial conditions. That is un plus 1 is equal to L delta un, u0 equal to phi. That is the initial condition as defined at the initial time level, that is time level t equal to 0. And vn plus 1 is equal to L delta vn, means that both solution vector u and vn satisfy the same difference operator but with different initial conditions. Initial condition for solution vector vn is prescribed by the function psi, that is v0 equal to psi. So we can say that a finite difference scheme is stable if there exists a positive constant C which is independent of mesh spacing and initial data such that norm of un minus vn is bounded by norm of u naught minus v naught as n tending to infinity, delta x approaches to 0, delta t less than delta t approaches to 0 in finite time domain. So what does it mean? What is, do you mean stability? That is solution of a difference scheme do not grow unboundedly. So here, whatever bound you are having initially, what is the at the initial time level, so that bound will remain with the upper time level as well. So the requirement that C be independent of delta x, delta t, u0, v0 implies that bound expressed in above equation remain uniform. So the concept of stability implies that initial bounded difference. What is the initial bounded difference? Norm of u0 minus v0. Initial bounded difference between two solutions remain bounded for finite times when the mesh spacing is sufficiently small. That is that initial difference between the two solutions will remain bounded and do not grow unboundedly. Am I right? So that is if there is a small change in the initial condition, so there should be a small change in the finite difference approach, finite difference solution. If there is a large change in the initial condition, so correspond to that, that changes should reflect in the finite difference solution. Am I right? So that is there should be continuous dependence in the solution for finite difference scheme for the initial conditions. And also note that we are not claiming that that constant c should be bounded by 1, but that constant c should be independent of the mass spacing, mass parameters delta x, delta t, and initial data. So nothing in the definition that c should be bounded by 1. Contrary to a notion of stability that arises in physics and engineering, some growth of the difference between solution is permitted. Okay. Now, alternative definition of the stability. A finite difference scheme 7. What is the finite difference scheme 7? Un is equal to un plus 1 is equal to L delta un. So basically, if we are able to bound the growth of this matrix L delta in some norm is bounded by something. So in that case, we can say that our finite difference scheme is stable. So a finite difference scheme, this one for a homogeneous initial value problem is stable if there exists a positive constant C independent of matrix L delta in some norm. So if we are able to bound that matrix in some norm, then we can say that our finite difference scheme is stable. Also note that a consistent finite difference scheme for a given PD is said to be of order P in time and Q in space if truncation error is equal to order of delta t to the power P plus order of delta x to the power Q. So in terms of this definition, our constructed forward time central space scheme is second order accurate in space and first order accurate in time. So here, with the help of above definition, first we will show that our forward time central space scheme for heat conduction problem is stable in maximum norm provided r less than equal to 1 by 2. That is, our FTCS scheme is not unconditionally stable. It is conditionally stable. That restrictions should satisfy by FTCS scheme for the stability, and that restrictions also lead to a severe restriction of the step size in time direction. Delta t should be of order of delta x square due to this restriction. Okay, so here, to prove stability of FTCS scheme, we begin by taking the absolute value of the difference scheme and using the triangular inequality to obtain. Because of our finite difference scheme is uj n plus 1 equal to r uj minus 1n plus 1 minus 2r uzn plus r uj plus 1n. Take the absolute value of both sides and then use the triangular inequality. You can get this kind of equation. Since and we know that r is positive. R is positive. Why? Because alpha is positive. Sigma is positive, not alpha. Thermal diffusivity is positive. Sigma is positive. Delta t time step is positive. Delta x space step is positive. So that implies r equal to sigma delta t over delta x square is positive. And also note that if R lies in the semi-open interval 0 to 1 by 2, all coefficient of the finite difference scheme are non-negative. That is, R is positive, R greater than 0, and 1 minus 2R, that is also non-negative. So in that case, that equation reduced to this equation uj n plus 1, which is less than equal to R use a minus 1n plus 1 minus 2r use a n plus r use a plus 1n. And note that use a minus 1n, use a n, use a plus 1n. These are the sum term of the vector un. Of course, all these terms will be bounded above by the norm of vector un in maximum norm. In maximum norm. So we can say that this equation will be less than equal to r norm of un infinity plus 1 minus 2r norm of un infinity plus r norm of un infinity. So taking norm un infinity outside, r plus 1 minus 2r plus r. So 2r and minus 2r will be cancelled out. So ultimately we are having u j n plus 1 is bounded above by infinity norm of vector un for all j. Now note that this inequality is true for all j. J run from 1 to capital J minus 1. So of course, this inequality will be true for the vector u n plus 1 at the n plus 1 at time level. So thus it means this inequality must hold for all value of j that maximize its left hand side. Am I right? So it should be true for the maximum norm of vector un plus 1. Am I right? So in this way, we are able to show that norm of un plus 1 is less than equal to norm of un. So in this way, we can show the stability of the FTCS scheme. So that is norm of un plus 1 infinity less than equal to norm of un infinity. And that implies norm of un infinity is less than equal to norm of u0 infinity by iteratively. Am I right? Norm of un infinity will be less than norm of un minus in 1 infinity. Norm of un minus 1 infinity will be less than equal to norm of un minus 2 infinity, and so on. We are getting this result. So which establish the stability of the FTCS scheme for heat conduction problem. Now next, we will show the convergence of the FTCS scheme. Here we will show that FTCS scheme for heat conduction problem is convergent with order of delta T plus delta X square, provided R should be less than equal to 1 by 2. So here we have this FTCS scheme for the heat conduction problem for J, where J run from 1 to J minus 1, that is at xjtn point, and the heat equation solution satisfy continuous solution satisfy this equation. So since this is a continuous solution, so we have truncation error term also over here, delta tau jn, j run from 1 to j minus 1. Now letting en equal to uzn minus uzn, that is the error term in our solution. So if we define error by taking the difference between continuous solution and finite difference solution at xjtn point, and if we denote it by en, so we are getting and subtracting this equation, first equation from second equation, and then taking the absolute value of both sides and using the triangle inequality, we can get that kind of relationship in between error terms at n plus 1 at time level and n at time level. Am I right? Now replacing the error term on the right hand side of the above expression, because of this r is positive, mod r is equal to r, and for r less than equal to 1 by 2, 1 minus 2r is also positive. mod r, that is also r is positive, so mod r equal to r, so you can take it directly. So if we replace mod of ej minus 1 and mod of ej and mod of ej plus 1 and by their maximum norm at nth time level, that is by their maximum value, which we are denoting by this norm en in maximum norm, and truncation error, absolute value of truncation error, if we denote in infinity norm, replace this by in infinity norm. So norm en plus 1, that is it will be less than equal to this equation, and this equation will be less than equal to mod of r plus mod of 1 minus 2r plus mod of r inside the bracket into norm en infinity. All these term will be replaced by their maximum value, that is norm of en infinity plus delta t norm of tau n infinity, j equal to 1 to j minus 1. We know that r is positive, and if in addition r is less than equal to 1 by 2, then 1 minus 2r is greater than equal to 0. So mod of ej plus 1 n will be less than equal to norm en infinity plus delta t norm of tn infinity. So since j equal to 1 to j minus 1, so since this inequality is true for all j equal to 1 to j minus 1, so among them, among correspond to any j, you may have maximum value of mod ej n plus 1, that is which will be equal to norm of en plus 1 infinity. So that inequality is also true for the maximum norm for this vector en plus 1. So norm en plus 1 infinity, this is a vector norm, infinity norm, will be less than equal to norm en infinity plus delta t norm tau n infinity. Now iterating, so thus we are having this relationship. So further, norm En infinity, you can say that it will be according to this relationship. Norm En infinity will be less than equal to norm of En minus 1 infinity plus delta t norm of tau to the power n minus 1 infinity. So you can further iterate norm of En minus infinity, and continuing in this way, we are getting that kind of relationship. Iterating this inequality over n, norm En plus 1 infinity will be less than equal to norm En minus 1 infinity plus delta t norm tau n infinity plus norm tau n minus 1 infinity, which will be less than equal to norm en minus 2 infinity plus delta t inside the bracket norm of tau n infinity plus norm of tau n minus 1 infinity plus norm of tau n minus 2 infinity, and so on. So iterating in this way, we are getting this kind of error equation, inequality, error inequality. Norm of En infinity will be less than equal to norm of E0 infinity n times delta t tau, where tau is nothing. Tau is we consider maximum over the maximum of norm of tau to the power k infinity, where k vary from 0 to n minus 1. So that error inequality we are getting from this one. So what is norm of E0? E0 is equal to vector E0 is equal to continuous solution vector U0 at the U minus finite difference solution vector U0. And you know that continuous solution and finite difference solution satisfy the same initial condition at the initial time level. So that's why E0 will be equal to 0. So solution of the PD and difference equation both satisfy the same initial condition. So norm E0 infinity will be equal to 0. Additionally, if T is the total time, that is total time of interest, that is final time T. In that case, N delta T will be less than equal to T for all combination of N and delta T. So thus that error inequality take this form: norm E n infinity less than equal to t tau. So where tau is nothing, tau is the bounded by delta t by 2 k plus sigma delta x square upon 12 n, where k is the maximum of ux utt, k is the maximum of utt, and m is the maximum of fourth derivative of u with respect to x over the whole rectangular domain. Our rectangular domain is this: t vary from 0 to t and x vary from 0 to 1. So that kind of rectangular domain, this is the 0 to 1, and this is the final time t, and this is the initial time level, this is the first time level 1, this is the say and so on, this is the say, let's say, nth time level, this is the first mass points in time direction, x1 x2 and so on. So that's why we are having that grid of finiteness. So over the rectangular domain, we consider second derivative of u with respect to t is bounded by k, that is k is the maximum value of this, and m is the maximum value of fourth derivative of u with respect to x over this rectangular domain. So using that thing, we can say that norm E n infinity is bounded by this: t delta t by 2 k plus sigma delta x square upon sigma delta x square upon 12 into m. So here again you can notice that if we are letting delta t approaches to 0 and delta x approaches to 0, that is if we continue to refine the mass in both the direction, space direction and time direction, then that error in our solution approaches to 0 in infinity node. So what does it imply? It implies that forward time central space scheme converges to the solution of the heat conduction problem in the maximum node. So, and provided r less than equal to 1 by 2. So as we define the here convergence of the finite uh, convergence of the finite for finite difference scheme. A finite difference approximation converges to the solution of a PD over a finite domain in a particular vector norm if that difference between the continuous solution vector and finite difference solution vector approaches to 0 in any norm, in any particular vector norm approaches to 0 as we continue to refine the mass, then you can say that difference approximation solution u, capital U, approaches to the continuous solution u. So here convergence of FTCS scheme we have shown here in the maximum node. Okay. So now, according to maximum principle, a sufficient condition for stability of the one level finite difference, that scheme, FTCS scheme, that is a one level scheme, because they are involved only uh, 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 grid solution. We are looking solution at the previous time level only, n or n plus 1 at time level. So if we look to find the solution at n plus 1 at time level, we look solution at the n or n minus 1 at time level. So then that kind of a scheme is said to be two level scheme. So it is the only one level scheme. So for a one level scheme, sufficient condition for stability of that kind of finite difference scheme is that all these coefficient Cs in finite difference scheme, Cs should be positive, and and if you are summing them, then their sum should be add to unity. And we already seen that for our FTCS scheme, coefficient r 1 minus 2 r, and if condition r less than equal to 1 by 2, then this condition of maximum principal are satisfied for the FTCS scheme. R is positive, 1 minus 2R is also positive if R less than equal to 1 by 2 lie in the semi-open interval 0 to 1 by 2, and if you add them, their addition will be equal to 1. So a sufficient condition for stability of the one level finite difference scheme of that kind use a n plus 1 is equal to summation mod s less than equal to s cs use a plus s n in the maximum norm is that all coefficient cs should be positive and addition of them should be unity. Okay, now I am going to discuss the matrix method for the stability analysis. So here mainly we have three kind of method for stability analysis. One is the maximum principle. Another is the von Neumann stability analysis, which will be discussed by Professor Ashish tomorrow. Fourier analysis method, or which also known as von Neumann stability analysis method. And one another kind of stability analysis method is the matrix analysis method. So there are few drawback associated with each method. So for example, the maximum principle require finite difference scheme to have positive coefficient and their sum should be 1. So in practice, most for many finite difference scheme, that kind of conditions is to satisfy becomes very difficult. And also in the von Neumann stability analysis method is applicable with the constant coefficient linear problems only with periodic initial data. For example, if you are constructing finite difference scheme for such problem which is having variable coefficient. So in that case, if you want to apply von Neumann stability analysis, you have to assume that those variable coefficient is bounded by some positive constant quantity, and correspond to that you have to analyze your finite difference scheme using von Neumann stability analysis. So von Neumann stability analysis method require constant coefficient linear problems with periodic initial data. And this matrix stability analysis method can be used to analyze more general linear problems. In fact, for variable coefficient problems, matrix analysis method can be used. So, with the goal of describing matrix analysis method, we consider a finite difference scheme of this form, which I already written in equation number 7, un plus 1 equal to L delta un. For simplicity, we assume that that difference operator L delta, where L delta is nothing, that is a matrix in our case difference. So we are calling it as a difference operator that should be independent of the time level n. So we can iterate this scheme to obtain this thing because un will be equal to L delta un minus 1. So iteratively n times you are getting un equal to nth power of L delta into u0. u0 is the initial vector which is correspond to the initial condition defined at the initial time level. Okay. Now taking any norm of both sides for this equation un equal to L nth power of L delta u0, taking a norm of both sides, norm you are getting, and using that property of matrix norm of ab is less than equal to norm of a into norm of b, norm of L delta and u0, that is a initial vector. So initial vector you can consider as a matrix. So this will be less than equal to norm of nth power of L delta into norm of u0. So that implies norm of un should be less than equal to nth power of L delta into norm of u0. So what does it mean? Your finite difference scheme is stable if you are able to bound the growth of this term, that is you are able to bound this nth power of L delta in some norm. That is, the finite difference scheme 7 is stable if and only if there exists a constant c such that norm of nth power of L delta is bounded by c as n tending to infinity, delta x approaches to 0, delta t approaches to 0 over the finite time domain. ठीक है. So as n tending to infinity, basically n tending to infinity, delta t definitely will be approaches to 0, and represent here the number n stand here that correspond to the time level n at time level. Okay. So using matrix stability methods, here we will try to limit the growth of norm of L delta. So before beginning, first we review some material about the matrix eigenvalue problem. As I already said that spectral radius rho L delta, radius of any given matrix A is defined by the largest eigenvalue in magnitude. ठीक है. So here spectral radius rho L delta for the matrix L delta is the modulus of its largest eigenvalue. So rho L delta is defined by the largest eigenvalue in magnitude for the matrix L delta. ठीक है. And there we define the norm of two norm for a matrix A. So two norm of a matrix A is defined by the square root of spectral radius of matrix A transpose A. So here in the next lemma, we will show that spectral radius provide a lower bound for any matrix norm. So here in this lemma, we will show that thing. Here, let rho L delta and norm L delta be the spectral radius and any vector induced matrix norm of L delta. Then this spectral radius for matrix L delta provide the lower bound for any vector induced matrix norm for the matrix L delta. So we will prove it in this lemma. So you know that if lambda I and this xi is an eigenpair for the matrix L delta, then by the relationship Ax equal to lambda x, that matrix that eigenpair will satisfy this relationship L delta xi equal to lambda I xi. I run from 1 to n. That is, if xi is an eigenvector of L delta correspond to the eigenvalue lambda I, then of course by that relation Ax equal to lambda x, L delta xi will be equal to lambda I xi. Now if we take norm both side for this equation, norm of L delta xi will be equal to mod of lambda I into norm of xi, I equal to 1 to n. This is true for all eigenvalues lambda 1, lambda 2, lambda n correspond to eigenvectors. Am I right? So that gives us mod of lambda I is equal to norm of L delta xi upon norm of xi. Xi is a vector, L delta is a vector. So using that using that property of matrix norm again, L norm of L delta xi will be less than equal to norm of L delta into norm of xi. Norm of xi will be cancel out. So ultimately you will having mod of lambda I will be less than equal to norm of L delta. And this is true for all eigenvalue lambda 1, lambda 2, lambda n. I run from 1 to n. Since this inequality is true, mod lambda I is less than equal to norm of L delta. This inequality is true for all eigenvalues. So among them, this is true for the largest eigenvalue in magnitude. So largest eigenvalue in magnitude is defined as the spectral radius. So this inequality gives the desired estimate. Rho L delta will be less than equal to norm of L delta. Okay, and also we know one another important property if lambda x is an eigenpair for a matrix A, am I right? Then lambda to the power n x will be an eigenpair for the matrix A to the power n. That is, if lambda is an eigenvalue for a matrix A, then lambda to the power n also will be an eigenvalue for the matrix A to the power n. So using that thing here, we obtain this lemma. Since the eigenvalue of nth power of L delta are nth power of lambda I, ठीक है, if lambda I is an eigenvalue of L delta, then lambda I to the power n, lambda I to the power n will be an eigenvalue of L delta to the power n. Am I right? So that's why spectral radius, nth power of spectral radius of L delta, because here in the last lemma we proved that rho L delta is bounded by norm of L delta. Am I right? And we know that lambda I to the power n will be eigenvalue of L lambda L delta to the power n. Am I right? And among them, if rho L delta is the spectral radius of the matrix L delta, that is largest eigenvalue in magnitude for the matrix L delta, then rho to the power n L delta definitely uh, satisfy the lower bound for the norm of nth power of L delta. It means that rho to the power n rho to the power n define the lower bound for any matrix norm for the nth power of L delta because of this thing. And then using that relation, norm of AB less than equal to norm of A into norm of B. Norm of nth power of L delta can be written as norm of L delta into L delta n times, and which will be less than equal to norm of L delta into norm of L delta using that relation. Norm of AB is less than equal to norm of A into norm of B. So norm of nth power of L delta will be less than, using this inequality, will be less than equal to nth power of norm L delta. So thus what we are having, nth power of spectral radius of L delta is the lower bound, or is the lower bound of nth power of any matrix norm of L delta. So look this equation. So here the left and right side of 9, equation number 9. So here left side gives you the necessary condition for the stability of a finite difference scheme, and this right hand side gives the sufficient condition for the stability of the finite difference scheme. So necessary stability condition is also known as the von Neumann necessary stability condition for a finite difference scheme. So a necessary condition for the stability of the linear homogeneous finite difference scheme is that there exists a constant C independent of delta x, delta t, satisfying spectral radius of L delta should be bounded by 1 plus C delta t. So any finite difference scheme or linear homogeneous finite difference scheme, if it is stable, will satisfy this condition. Note that this is a necessary condition, not sufficient. If this condition is satisfied, it is not it is not necessary that scheme will be stable. But if any scheme is stable, then that condition definitely will be satisfied. So to prove this theorem using equation number 10, we see that rho n L delta is the bound of nth power of matrix norm of L delta. ठीक है? And note that here our aim is to bound the growth of L delta. So note that here rho and L delta must be bounded, otherwise norm of nth power of L delta could not be. Note that if look this equation number 10, that equation number 10 is important. Here our ultimate aim is to get the bound of this term. Note that if spectral radius of L delta is not bounded, then definitely this term will not be bounded. So necessary condition for that this term is bounded, that spectral, that rho nth power of spectral radius of L delta should be bounded. Am I right? So using 10, we see that nth power of nth power of spectral radius of L delta, that is rho to the power n, must be bounded. Otherwise, this term could not be bounded. Thus, a necessary condition for the stability, because we know that our finite difference is stable if this we are able to bound of this term, and that bound should be independent of mass parameters and initial conditions. So this term is bounded. So for that necessary condition is that this term should be bounded. So thus a necessary condition for the stability of 7 is that there exists a constant C such that nth power of rho is bounded by C for all n delta t less than equal to t as delta x delta t approaches to 0, and that constant C should be independent of these mass parameters delta x delta t and initial conditions. Now taking the nth root of this one and using the maximal value of n gives, if you are taking the nth root of this, you are getting spectral radius of L delta must be bounded by c to the power 1 by n, and we know that n delta t is less than equal to t, so n will be less than equal to t upon n will be less than equal to t upon delta t, so 1 upon n will be less than equal to delta t is upon capital T. So c to the power 1 upon n will be less than equal to c delta t upon t. So when delta t is sufficiently small, so Taylor series expansion can be used to find a value of c such that this exponential term, this term c delta t upon t is bounded by 1 plus c delta t if delta t is sufficiently small. So in this way, we can prove the necessary condition for the stability. Next, I am going to discuss the sufficient condition for the stability. A sufficient condition for stability of the linear homogeneous finite difference scheme is that there exists a constant C which is independent of mass parameters and satisfying norm of L delta should be bounded by 1 plus C delta t. If we are able to find out that kind of bound in any matrix norm for over difference operator, then definitely our scheme will be stable. So as discussed earlier, so proof of this is again very easy. As we discussed earlier, after an iteration of the linear homogeneous finite difference scheme and then applying the norm of on both sides, we are having norm of un is equal to norm of L delta to the power n u naught, which is less than equal to, by using the property of matrix norm, uh, and norm of L delta to the power n and norm of u0. Further, using tan, we have norm of un, because norm of L delta to the power n is less than equal to nth power of norm of L delta. So using that equation number 10, we are getting this equation. Norm of un is less than equal to nth power of L delta into norm of u0. So next, using the given condition, norm of L delta is bounded by 1 plus C delta T. Here we will show that if this condition is satisfied, over scheme will be stable. That is, we have the bound for this one, norm of UN. So we have norm of UN is less than equal to 1 plus C delta to the power n norm of U0, which will be less than equal to 1 plus C delta T, and, and because of n delta T is less than equal to capital T. So n will be less than equal to T upon delta T. So it is less than equal to 1 plus C delta T to the power T upon delta T norm U0. Now, using the well-known limit formula for the exponential function, limit n tending to infinity, 1 plus x upon n to the power n is equal to e to the power x, we are having 1 plus c delta t up to the power t upon delta t. It can be rewrite in this way, 1 plus ct upon t upon delta t. That is, we multiply by t in numerator and denominator in this term, and writing t upon delta t. So using this formula, you can see that this term approaches to e to the power ct as delta t approaches to 0. Thus, we are having norm of un is bounded by e to the power ct norm of u0. Here, since c is a constant which is independent of delta x and delta t, and t is some fixed final time, total time. So definitely is to the power ct will be a some finite constant. It will be a some finite quantity, and c, that small c doesn't depend on the mass parameters, and t is some fixed final time. So definitely e to the power ct will be a some finite constant. So let this constant is denoted by m. Let m equal to e to the power ct. Then we are having norm of un is less than equal to m norm of u0. So in this way, we able to show that this is the sufficient condition for the stability for any linear homogeneous finite difference scheme. So if for our associated coefficient matrix, we are able to show that in any matrix norm, in any matrix norm, that matrix is bounded by that kind of quantity 1 plus c delta t, then definitely your scheme, linear finite difference scheme, will be stable. So next, I am going to state the Lax-Richmond equivalence theorem. That Lax-Richmond equivalence theorem state that to prove the convergence, if your linear finite difference scheme is stable and consistent, then it implies convergence. So this is a very famous result given by Lax and Richmond and is known as Lax-Richmond equivalence theorem. So it states that for a well-posed linear initial value problem and a consistent finite difference scheme, stability is both a necessary and sufficient condition for convergence. Means that consistency plus stability implies the convergence. So, and with this, I am going to conclude today's lecture. And also note that proof of this Lax-Richmond equivalence theorem is also easy. Like here in the example for forward time central space scheme for the heat conduction problem, I establish the convergence with the help of stability and consistency. So in the same line, you can show that if your scheme is consistent and stable, then it will be convergent. So same line you can easily prove this theorem. But another way is not easy to prove. If your scheme is not stable, then to show that your scheme is not convergent, then it is little bit difficult to prove. But proof of this other part of this theorem you can find out in the in that book authored by K.W. Morton. Consistency and plus stability implies the convergence that you can easily prove, and that proof follow the same way as I discussed the convergence of the FTCS scheme. But if your scheme is not stable, then your scheme will not be convergent. That proof, it is not a little bit easy, but you can found that proof in the book authored by K.W. Morton. So I conclude this lecture with this remark. In practice, convergence is difficult to establish, while consistency and stability are less so. Consistency merely requires the use of Taylor series expansion, and stability can be proven at least in simple situations using maximum principle, matrix analysis approach, or von Neumann stability analysis method. Thus, this Lax-Richmond equivalence theorem provide a very useful information. So I conclude today's lecture with giving a tribute to P.D. Lax. He was a well-known applied mathematician, and in fact, given numerous results in the computational PD. For example, Lax Milgram lemma, which is the backbone of the finite element method analysis, Lax Van scheme, Lax Friedrich scheme, and this Lax Richmond scheme. So was a well-known Hungarian-born American mathematician and a Nobel Prize laureate. Worked in the area of pure and applied mathematics, and he recently died in the age of 99, just last month on 16th May 2020. So tributing with tribute to P.D. Lex, I am concluding this today's lecture. Any question from these are some references. So basically I follow these books to prepare these notes, this lecture. Thank you.
Thank you, Professor Vikas, for a very informative and very nice lecture. Participants, if you have any question, you can write in the chat box.
Any question from your side, participants?
Please write in the chat box if you have any question.
Any query regarding any proof? Just with the simple tool, I try to make understand you about the concept of consistency, stability, and convergence. Okay, thank you, Professor Rahul.
Okay, yes, thank you, Professor Vikas. Indeed, it was a nice lecture, and if possible, if you have any material to be shared with our participants,
Yeah, today
you can share.
today I will share both slides for yesterday lecture and today's lecture after removing some typo error. So today or
Yeah,
tomorrow I
sure,
will
sure.
share you both slides.
Okay, no issue. Please
Okay.
take your time. And participants, tomorrow again we will be meeting around 10 a.m. in the morning. And tomorrow we have the session from
Okay.
like we have session, we will be having lectures from 4 to 6. Okay, so as I told you earlier, although all the participants, tomorrow in the evening lecture, which was earlier from 6 to 7, that has been preponed to forenoon session from 1 to from 1 to 2. Okay.
Okay, thank you.
So, yeah, with this we can conclude, we can close this session now. And
Okay, just I am looking,
participant.
Professor Rao, just I am looking at the chat. So there is some query from Satyendra.
Mm-hmm.
Satyendra, so if I am correct, I will not cancel out, but less than delta del L. So first consistency, then stability, then only convergence. Yes, 4 lakhs. Yes, Satyendra, any specific query? Yeah, consistency plus stability implies the convergence. It is said by Lax equivalence theorem. Okay. Okay, thank you, Dr. Rahul.
Yes. Okay, sir. Okay. Yeah, we can close the session now.
Okay.
Yeah. Bye bye.